Hi, today we're going to be talking about the mean of a continuous distribution. So let's take as an example uh, this familiar density function. So our goal is to calculate e of x here, which is the mean and given by that symbol. Um, Here, the density function is going to be this familiar uniform distribution. Let's just take a look at the graph of this density function. Okay, well, if you're looking at this density function, you're going to say, oh, it's symmetric, like it's completely even, so the expected value here, well, that's going to be this value of 2. That's going to be e of x. And you'd be 100% correct. How could we get an e of x of 2? Well, before, so if it for a discrete distribution, we just summed up everything. We had the summation. But for a continuous distribution, well, there's lots of little things to sum up. Like I can subdivide these intervals into many different subdivisions and add it up. None of them will be the exact until I take infinitely many subdivisions, and in that case you get an integral. Okay, so if I want to calculate expected values, is given by summing things up, i.e. taking the integration, and we integrate x times f of x dx. The x times f of x part, that's familiar. That's the familiar part of what we add up. How we sum it up is now with an integral. You might say, oh, I have to integrate from minus infinity to infinity, but remember, f of x is only non-negative from 0 to 4. So we need to calculate that. We've seen, and there's the x there, x over 4, my apologies. We've seen how to anti-differentiate x. That'll be x squared over 2 times 1/4 integral from 0 to 4. So 1/8 times, we plug in the upper limit, we'll get 4 squared minus 1/8 times by the lower limit, 0 squared. So this will be 16 divided by 8, that's 2. Gave us exactly the right answer. Okay, so that is the mean 2. Let's do some other examples. What else could we do with expected value? We could calculate, for instance, the variance of x. The variance of x is x squared minus mu squared. We've already seen mu squared is 2. We just need to know what e of x is. Well, e of x is, as you would guess, intuitive. Instead of integrating x, we'll integrate x squared. Okay. And we're going to get integral from 0 to 4, x squared over 4 dx. We'll integrate the x squared and we'll get x cubed over 3 times 1/4. Evaluate at 0 and 4. We'll plug in the 4, we'll get 4 cubed divided by 3 times 4 minus, when we plug in 0, everything's 0. So we'll get 16 thirds. So we'll get 16 divided by 3 minus 4. Okay. Well, when you do this calculation, you're going to get 1.33 as your final answer. Okay. So I just wanted to also highlight e of x squared as this more generally. The expected value of a function of x, as you guessed it, is the integral from minus infinity to infinity, just a fancy sum, of h of x times the density function f of x dx. Okay, that's the general rule, and that's what we've used above. So if I'm asking for the moment generating function, it's still the same definition. It's the expected value of e to the t times x. So h of x is exactly that thing inside. And that will be this integral from minus infinity to infinity of e to the t times x times f of x dx. Now we don't have to integrate from minus infinity to infinity. We just need to integrate from 0 to 4 e to the t times x times 1/4 dx. We can anti-differentiate this. Remember, t is treated as a constant. So we'll get e to the t times x over t times 1/4, evaluated at 0 and 4. And then we plug in x equals 0 and x equals 4. So let's do that. E to the 4t divided by, 4t minus e to the 0, which is 1. Okay, so e to the 4t minus 1 divided by 4t, and that is our moment generating function in this instance. Okay, so this is how we calculate moment generating functions with that formula. So these things in boxes you'll use in different scenarios. Okay, thank you very much.